So in the last classes we talked about different ways how you can convert words into vectors. Now all of this is good, but here is the thing. When we talked about this, right, we discussed about algorithms that were based on the frequency. So frequency algorithms or frequency methods, and they were more like TF, IDF, bag of words and so on, right? So all these are fine, but here is the thing, right? They do not understand the context of a word. So you might know that in any language context is very important. So suppose there is a whole sentence, okay, and then there is a word. So that word in that particular sentence might mean something, and in a different sentence it might mean some other thing, right? So the whole context of the story is very important to understand the whole thing. Hence, to solve this problem, what happened was basically we came across something that are known as predictive methods. Okay, so now what we are going to do is basically discuss about these predictive methods. So what predictive methods basically do is basically they understand the importance of a particular word in a particular sentence, in a paragraph or so on, right? So if we talk about bag of words, right, so in that case what happened was we basically counted the frequency of, let's say there is a word lady, so we'll be counting the frequency of lady, okay, but you need to understand the context of it. So you need to know that lady is very similar or very related to woman. Now that you cannot understand based on just the document itself, right? You need to understand the context of the thing, you need to understand the English language behind it and so on. So then again in the same way you would be able to say, okay, so that makes it that a guy is very much related to a man, right? So this basically, this understanding of context, right, so this cannot be done using a bag of words or TF-IDs, because those are frequency based methods. They understand what happens using the frequency of it, okay, they do not understand the whole thing. Hence what we will be doing is basically we'll be understanding predictive methods, and what we'll be understanding about is autoencoders first. So autoencoders are another part of your neural network, so they are other neural networks, okay. So right now if we talk about neural networks, we have talked about MLP, multi-layered perceptrons, then we have talked about CNNs. Now we are going to talk about autoencoders, right? And even in CNN we have discussed about a lot of things, so we're gonna just keep it there, and now we'll be talking about autoencoders. So what autoencoders basically are, or what we will be talking about autoencoders is basically how we can use it for text embedding. So text embedding basically is converting your text into vectors. So you can convert your text to vectors, and even though it has been converted into vectors, right, you will have one more thing here, okay. So you have converted your text into vectors, but at the same time it will understand the context in the way it has been converted, okay. So what that means is, like I said, how a lady is related to a woman. So the difference between the vectors of lady and woman is going to be very alike when you compare it with the differences or the distances of a guy and a man, alright. So that is what text embedding means. Basically it helps you in predictive, obviously in autoencoders, using autoencoders, what it means is basically it helps you to understand how two words are related to each other, how they are not related to each other, and so on, alright. So that is what you can understand using autoencoders. So we are going to talk about what is known as word to vec. So word to vec, as the name suggests, is basically converting the words to vectors, alright. So we are going to, in the next few classes, talk about word to vec and how this is done, alright. But here is the thing, this is the catch here. Since word to vec, we cannot discuss about the whole thing without understanding the architecture of it. Hence what we are going to do is we are going to talk about autoencoders today, okay. So the whole discussion about today is going to be on autoencoders, the different types of autoencoders, how they are, how the architecture works, and so on, alright. So this is your basic autoencoder structure. These are all your inputs. This is your bottleneck features here. This is your also hidden layer, and then these are all your outputs. Okay, so this is basically the structure of an autoencoder. So here is the interesting thing about autoencoder if we talk about, alright. So if you talk about an autoencoder, here your input is basically x, x1, x2, x3 and so on, right? So these are your inputs. Your outputs are also x1, x2 and x3. That means these are your inputs and these are the label values. The label and the input are the same, okay? So our task is, what our basic task about autoencoder is, or this can also be known for its compression. Okay, so these are also compression types of algorithms. So what it does is basically, this is your input, you have to produce the same output here, okay? So your output should be equal to your input, but you have to do that when you have decreased the number of neurons, okay? So now you have to compress your input in such a way, right? So your input needs to be compressed in such a way so that it is able to create your output as it is with the input, okay? So now what will happen is, instead of using such a big input, you can use a small input to create your actual values. So that is basically the whole thing about autoencoders. So let's say you have V inputs here, and this is your n dimension, and this is back to V inputs. So you have to compress all the V inputs in such a way, and by the way, V is greater than n, alright. So you have to compress your V inputs in such a way so that it is, you have compressed it in this n dimension, and now using this n dimension output you have to create all these V dimensions back, okay? So you have to preserve as much of the values as possible. That is basically the whole point of this. So you have to preserve by decreasing the dimensions. That is the whole thing, okay? So now here is the thing, you might remember this. So if you have learnt about machine learning, you might know about something known as PCA, right? And not just PCA, you also have t-SNE and stuff. So the main task of these things are basically to reduce your dimensions, right? So reduce dimensions, but that is done using variance. So you have to preserve your variance. So you have to get as much of variance as possible, and that is the whole task or whole point of PCA and t-SNE. Now this is the same thing that is done using your deep learning methods, okay? So this is an algorithm. What it does is basically, your input will be same x once, your output will be same x's, okay? So your task is basically to create what was there in the input with as less of dimensions as possible, okay? So that is basically the whole point of this autoencoder, alright? So what this means is basically, if you have, let's suppose, and all these are by the way fully connected layers, you can see here these are all fully connected. So what that means is, let's suppose you have x1 and it has V dimensions. So here what will happen is basically it will be converted to n dimensions. If you think about the weight matrix here, right? So the weight matrix in this case would be 6 cross n, because you have 6 inputs. If you see here, 6 inputs, and then you have an n dimension here, right? So the weight matrix will be W 6 cross n. And in the same way, if you think about it, since the weight matrix here is 6 cross n, here what will be the weight matrix? Here it will be n cross 6, W n cross 6, right? So this basically is your weight matrix now, the new weight matrix. So how will this look like if you think about it? So by the way, I am just assuming that you have 6 inputs. You can have as many inputs as possible. Since I don't want to take 2 different new variables, hence I am taking this as 6 because this is there in the question itself, okay? So how will this look like now? So that means it will have n rows. So 1, 2, 3, 4, this goes on till n, and it will have 6 columns. So 1, 2, 3, 4, 5 and 6. Now if you think about it, okay, if you think in this manner, you will realize one thing. See, each column here, each column is corresponding to this value here, because you have 6 columns. So each column will be corresponding to one value here, 1 from x1, the next will be again from x2. So this is x1, this is for x1, this is for x2, this is for x3, x4 and x5. Initially, if you think about it, it had V dimensions. Now what has happened? It has n dimensions. N is smaller than V, right? So in that case, what has happened is, now since each row is n dimension, So that means each of your x value or each of your input value has now been converted into n dimensions. N dimension, by the way, is smaller than your actual v dimension that it was happening. Okay, so that is basically what happens here. Alright, so this is the whole point of this. Okay, here 6 has nothing to do with it, I'm just saying. Okay, 6 has nothing to do with it, it has x dimension. 6 is the basic number of inputs here. Okay, so the whole point of this, let me revise again what happens. See, you have all your inputs here, you have one here bottleneck features, and then you have your output features. Your whole point of bottleneck is basically to compress your input as much as possible so that you can generate the input as it was using your output. Okay, that is the whole thing. Okay, so now you have the inputs, you get a weight matrix. Here the weight matrix is basically the number of inputs multiplied with the number of outputs. Okay, so this becomes W 6 cross n. Here your weight matrix will become W n cross 6. Okay, now this n cross 6, we can see how it can be represented here in this manner, right? So now that it has been represented in this manner, what we can do is basically for each column, so each column will now here represent what? Each column will represent one value from here. Okay, and since now the dimensions has reduced, so each column is now of what? N dimensions, because if you think about the matrix, it is n dimensional. So now what you can do is basically you can use these numbers that you have generated here or these vectors as your word embeddings. Alright, so this is basically the whole point of autoencoders. Okay, and by the way, even if you get the outputs, these outputs are of no use, unlike basic or other neural network models where outputs are very important. Since the outputs are equal to the inputs, we do not require the outputs. The outputs are just required to create this Wn cross 6 matrix, because this is the matrix that we will be using, or the one that we will be using to understand what is the actual embeddings. Okay, so this is all about autoencoders. Now what we are going to do is we are going to talk about some different types of or some different variances of autoencoders. So here we have an undercomplete autoencoder, AE. Okay, so this is an undercomplete autoencoder. So what does that mean? See, you have an input here. Instead of using just one layer that they have done, right? Instead of using that, what we can do is we can add many layers. Okay, so let's suppose this is 256 dimensions. Okay, here this is 256 dimensions. So instead of directly going to, I want something of 50 dimensions output. Okay, so I want that all my word embeddings be represented in 50 dimensions. So instead of directly going from 256 to 50, what I can do is I can first reduce it to 100 dimension, and then I can go to a 50 dimension. Then here also this will be a 100 dimensional, and this will be a 256 dimension. So here is the whole thing. Whatever number of dimensions you want for your text. Okay, so you want to represent your text in a vector form, and whatever is the dimension of the vector, that has to be your number of n. Okay, so the number of neurons here will be equal to the number of dimensions that you want. Okay, so you need to remember that. That is one thing I forgot to mention, but yeah, it is important. So basically what it does is, instead of going from 256 directly to 50, what it first takes a jump to 100 and then it goes to 50. These type of autoencoders are known as undercomplete autoencoders. So you do not have to directly preserve a lot of things. The computer can take one step at a time and then understand how this 50 dimensions has come across. Okay, so here also these all are fully connected layers. This is W, this is 6 cross n, whatever, let this number vocabulary be capital V. So this is W capital V cross n. Here you will get, since this is 100 dimensions, so you are going to get what? W 100 cross 50, you're going to get W 50 cross 100, and so on. Then you can use these values to actually represent what was here. Okay, so this is basically the whole point of undercomplete autoencoders. So now we have the next type of autoencoders. These are known as sparse autoencoders. So what are sparse autoencoders? See, if you think about this, as the name suggests, it gives you sparse values. Okay, so here is the thing. Your input can be dense or it can be sparse. That is up to the input. Okay, but if you want sparse outputs, you can use sparse autoencoders. So in that case, what happens is a very few of these neurons will be activated. Okay, and the ones that will be activated will have L1 regularization. if you have heard about if you have read machine learning and everything, you would know that L1 regularizer is basically used to create sparse values. Okay, so hence that will be used, and then you will get sparse autoencoders. So these regularizations, what they do is they help so that now you can preserve your values even more, and your model does not do what is known as overfitting, right? So since you do not know the number of neurons that you are going to use, right, since you do not know how much of this is going to be used, hence to prevent that, so you do not compress and lose a lot of values, at the same time you do not take a lot of values, that means the model is not learning anything. In that case, what you can do is you can use these L1 regularizers in sparse autoencoders. And then you have the final autoencoder, that is the denoising autoencoder. So as the name suggests, denoising autoencoders means you will be feeding corrupt value or corrupt input into the autoencoders. Corrupt input means what? Input where you have added the noise to it. Okay, so why is that important? See, here is the thing. You might, in real world, you might not get such clean data, alright? There is no chance you are going to get such clean data. In that case, what you have to do is basically, you have to make sure your model is robust to noises, because your data is going to be in this format. It can be in this format. In that case, you need to make sure your autoencoder or whatever neural network that you are using is robust to noise. So despite your input not being a very clear input, your model can still understand what is happening. Okay, so what it does is, you have an input image, you add noise to it. Okay, so now this is a corrupt input. Now these corrupt inputs will be passed through the autoencoder. Here the only difference is, instead of getting the input value as the output value, you will be getting the actual clean values. Okay, so now your model has understood, okay, so these are noise values, I need to remove these to find or to create or generate these clean values. Okay, so that is one thing. So now your model will be kind of robust to different noises. So now there are other types of autoencoders. If we talk about, you have variational autoencoders, and there are a lot more other things. Okay, but we do not require this, because here is the thing, we are talking about embeddings here, we are not talking about autoencoders. I just needed to give you an example of what autoencoders are, how they work, how the whole system is applied and everything, so that you might understand about how word embeddings work, and especially word2vec. So here is the thing, see, you had your different sentences. Your first thing that you do is pre-processing. How do you pre-process? So your pre-processing can be done in different ways. Removing stop words, cleaning your data in other formats. Okay, once that has been done, you have to pass it through a tokenizer to tokenize the values. Then you have to convert it into embeddings. Once that has been done, in that, then what you can do is basically pass it through a model, so an NLP model. So this is how you treat text. Now this is the very simplest form of it. The things are way more complicated than this, but yeah, this is the whole point of this. Okay, so we have talked about autoencoders. Let us go back and revise one more time what autoencoders are, what we talked about, and so on. So if we think about it, we talked about autoencoders. So what autoencoders do is basically compress the input in such a format so that when they create the output, regardless of this input, so even if you don't have the input and you are creating the output from these compressed value, you are able to save as much of the input data as it was initially. Okay, so how do you do that? Now you have weights, and we see how your weights have been assigned, and then we take the weights from here. Okay, it's from this factor we take the weights, and these weights are basically your word vectors. We understand how that has been found out. So this will be the this will how your it will look like. Okay, so this is a matrix that you get once you extract it from here, right? So this matrix, if you open it out, this is how it will look like. Okay, so you have n values here, and you have the number of inputs here. Okay, so here you have 6 inputs, hence you have 6 here. Okay, for each column, now each column will be an n dimensional value, and each column will represent one of the words or one of the input from here. This is how autoencoder works. Okay, then we talked about different types of autoencoders. So we talked about undercomplete autoencoders, where instead of directly going to the smallest value, we take steps at a time. We go to a less smaller value and then so on. Then we talked about sparse autoencoders, where L1 regularization is used to create sparse values. And then we talked about denoising autoencoders, where the whole task of this is basically adding noise to the actual value, deliberately adding noise, so that when you get the final value, your model is robust to noises. Okay, so I hope you understood the video, and I'll be seeing you in the next class, and keep learning.